Okay, we're going to continue on here, chapter 12. We're talking about bonding. And last time we talked about really sort of drawing Lewis structures. And remember, when you draw Lewis structures, there's some steps that you want to follow, especially when you're drawing them for covalent compounds, that will sort of get you to hopefully to the right picture. One of the most important things is to count up the total number of valence electrons. Remember that total number of valence electrons is really important because when your picture's done, you got to have exactly that number of electrons, no more or no few. The other important thing is sort of the logical arrangement of how everybody's attached to each other. So again, a couple of things that we talked about that will help you decide really who should kind of go in the middle and who maybe shouldn't go in the middle. It's usually the least electronegative atom that is in the center of the molecule. And again, in a lot of cases, things are attached directly to it. In other cases, there may be multiple central atoms. The organization of how you kind of do it is you usually kind of set up that skeletal sort of structure. The first thing you want to do is kind of do a single covalent bond from the center to each of the outside. That will obviously use up some electrons from your total. So in this case, you have two lines, so that is going to be 4 electrons. Whatever number of electrons are left over at that point, as we talked about, should go on in pairs on the outside atoms until they really do meet the octet rule, except for hydrogens, obviously should only have 2. If at that point you've really filled up all the outside atoms but still have electrons to put onto your picture, it's at that point they should then go on to the central atom, also in pairs of dots as well. Once you've really distributed all the electrons, you do want to make sure that you have met the octet rule. And it's really at that point, if you have not met the octet rule, that you want to try to fix it by either making a double bond first off, if not a triple bond to fix it. And a reminder that when we make something like a double bond, we're essentially going to take a pair of electrons and bring them in to make that double bond. And then we'll end up in this made up example here, something that looks like this. And everybody will hopefully have 8 electrons in this case. So if you follow that order, it really should get you to a pretty good picture in most cases. Again, you don't want to do it in piecework like we talked about. We also want to think about the electrons as sort of being distributed to everybody sort of equally along the way. We also talked about some exceptions to the octet rule, although in this class, we're really not going to come across any sort of exceptions that you have to draw to the octet rule. There are 3 exceptions. There's an incomplete octet, which means it has less than 8 around it, and really boron is an example of that. This is pretty much the most common example. It is perfectly fine with 6 electrons. There's also odd number of electrons where you end up with an unpaired electron. And probably the most common exception that you'll come across in sort of your chemistry journey will be in 1A, where you'll do a lot of the expanded octet. And the expanded octet are where you could go over 8, and that does happen around sulfur and sort of down on the periodic table. And those guys can go upwards of 12 electrons around it, or 6 pairs of electrons. And you do distribute it like normal. So for example, if you did have, something like this, and you kind of filled up all these outside electrons, and you still had electrons to go, they would also go on the central atom in pairs. It is sulfur on the periodic table to the right and left that has the ability to do that, and down because they do those d orbitals, again, to sort of house the extra electrons. As we talked about, I think last time as well, things in the period number 2 on the periodic table only have p orbitals, so they cannot go past 8 ever. So they always have to obey the octet rule. But in here, you should always obey the octet rule on anything you draw. We will not draw anything that will go above 8. But as soon as you go to 1A, you'll draw a bunch of stuff that will go above 8. Any questions on any of that stuff that we talked about last time there? All right, we're going to talk a little bit about geometry here, just to make sure we're all good. Molecular geometry, and we're going to talk about two types of geometry. One is sometimes referred to as the electron pair geometry, and it describes in sort of three-dimensional space how the electrons are arranged around the central atom. And there's one that's referred to as the molecular geometry. And that is also sometimes referred to as the shape of the compound or molecule that you're drawing. And that describes the overall shape of the actual molecule. Now, in some cases, depending on what type of electrons there are around the central atom, as to sort of, what type of overall shape you'll get. Now, if they're all sort of bonding electrons, you'll get a certain geometry. But if we have some non-bonding electrons around the central atom, it will allow a little bit more movement in the molecule, and that will allow for some different geometries to sort of occur. Now, as we will see as we go through this, in some cases, these names are going to be the same. In other cases, they will be different, really depending on those electrons. But it is all, when we do geometry, always about the central atom. So it's always about really the atom in the middle is always the one that you want to look at. Now, you can, as we saw, I think last time, have a situation where you do have multiple central atoms and you do it the same way. You just kind of do each central atom by itself, kind of individually. But it's always a central atom that you want to look at when you're doing geometry. Now, when we do geometry, it does refer to that three-dimensional arrangement. We can make a good prediction about the geometry here based on when we draw a good Lewis structure, what we see around the central atom. Really, probably the easiest way to sort of do that is look at two things. When you look at the central atom, a lot of times what we look at is we want to see how many electron pairs there are and how many bonds. And by knowing really from your Lewis structure how many electron pairs there are around that central atom and how many bonds there are, you will be able to sort of identify the geometry that should go with that molecule just based on really that two pieces of information. Now, the basis of this approach is what is sometimes referred to as the valence shell theory or the valence electrons theory. But basically, the idea is it's electrons, and electrons, frankly, are negatively charged. And when multiple electrons get near each other because they both have the same type of charge. But because they're being shared in a bond and they're around that central atom, they can't really escape. So they do have to kind of be near each other no matter what the situation is. So depending on the type of electrons that ends up near each other in sort of the central atom will result in some different shapes that we see. They're always going to try to do is essentially get away from each other. So as they are moving away from each other as best as they can, what that's doing to the overall shape of the molecule is it's actually changing as well. So as those electrons move, the overall shape of the molecule will start to change and will give us those different geometries that we do see. Now, the sort of name of this is VSEPR, which stands for valence shell electron pair repulsion model, hence the abbreviation. That's a long-winded one. And when we do geometry and follow this sort of model for geometry, there's really two types of models that we look at. There are ones where we look at the central atom and there's no pairs. Remember, lone pairs are non-bonding electrons. So basically, there's no dots when you look at your Lewis structure around the central atom. And then there are some molecules that do have dots, or lone pairs around the central atom. So they will have dots around the central atom. And depending on whether or not really those non-bonding electrons are there, will make a big determination as to whether or not or what type of geometry that we will see. When we do geometry, and really only when we do geometry, there's really two important things that we want to keep in mind. Because we're interested in how many electron pairs there are around the central atom and how many bonds there are around the central atom, if you have a double bond or a triple bond, when you go to count those guys, they count as one electron pair and they count as one bond. So regardless, when you look at the central atom to count up how many electron pairs, how many bonds, if it's single bonded, double bonded, triple bonded, it really doesn't matter. Everybody's counting as one, basically. They're essentially moving and working as one electron pair, even though they're double bonded or triple bonded, and they do count as one. That is really the major consideration when you do this type of geometry. The other one is about resonance structures, which we also talked about last time, which is, again, you can move the double bond electrons to some different locations. You could come up with some equivalent sort of structures. So most cases, if you apply this geometry here to any resonance structures that you draw, in most cases, you'll end up with the same geometry if you drew sort of a correct resonance structure along the way. But the major one is this: one electron pair, one bond. For anything that's a double, triple bond, just everybody pretty much counts as one when we're doing geometry. So let's talk about really the simplest geometry that you could have, and that is a diatomic molecule. And in a diatomic molecule, you only have obviously two atoms involved. And that could be something like H2, that could be something like F2, that could be something like oxygen, something like nitrogen, whatever it may be. They are only basically two atoms. So it's kind of like the old saying, the shortest distance between 2 points is a straight line. So because there's only two atoms, the only way you could arrange them is at opposite ends of a straight line, which means as soon as you see a diatomic molecule and you're asked, what is the geometry? That answer is linear. So the geometry is always going to be linear, no matter what the situation is. Again, doesn't matter if it's single bonded, double bonded, triple bonded, it will all be linear. Any questions on that? So it does get a little bit different when we start dealing with molecules that have three or more atoms involved. When we have three or more atoms involved, that's really where you want to go to the central atom and take a look at how many electron pairs and how many bonds that there are. So let's take a look at some of those here, or some examples of that. Okay, so once again, we're going to look at the central atom. We're going to count up how many electron pairs there are. Doesn't matter if they're lines or dots, and how many bonds there are. In this particular case, there are two electron pairs and two bonds when we do look at this guy. And it is the electron pairs around the central atom that determines the electron pair geometry. And the electron pair geometry with two electron pairs is also known as being linear. And when you take the electron pairs around the central atom and how many bonds there are together, that will give you your molecular geometry, which will be your shape. Your shape again. And that also will be linear in this case. You'll basically end up in a straight line as well. And the bond angle that you will have there between the three atoms there will be 180-degree bond angle. So when you have two electron pairs and two bonds, the electron pair geometry is linear, and also the molecular geometry for this guy will be linear as well. Any questions on that there? The next example is a central atom where we got three things attached. So once again, here we're going to look at electron pairs and bonds. And in this case, we are once again going to look at the central atom, and it has 1, 2, 3 electron pairs. And each of those are bonds as well, 1, 2, and 3 bonds. So something with 3 electron pairs in terms of the electron pair geometry, that is what is known as trigonal planar, or sometimes referred to as triangular, is what it's sometimes referred to. Now, something with 3 electron pairs and 3 bonds, the molecular geometry will also be trigonal planar. They call it triangular because basically it makes a nice equilateral triangle, basically, in terms of three-dimensional space. The bond angle between our 3 elements there is 120 degrees. So it makes a nice little triangle type of shape that occurs here. You do. So you're going to need to know the geometries and the degrees. Yeah. Other questions? Okay. Next example of geometry that you need to know is something with 4 things attached, like we have here in methane. And if we look at the central atom, once again here, we have 1, 2, 3, 4 electron pairs. And in terms of bonds, it will be 4. So something with 4 electron pairs is electron pair geometry, is what is known as tetrahedral. And because it also has 4 bonds with that, its molecular geometry will also be tetrahedral. Tetrahedral is sort of like a triangle on the outside there, and almost like a pyramidal type shape on the bottom. It has a bond angle of 109.5 degrees. If you're some older people, sometimes call it tetrahedron, but tetrahedral is what most books nowadays call it. A question on that. Up until this point, when we look at both the electron pair geometry and the molecular geometry for all these examples here, are they different names or the same names for each of those? The names are the same. So up until this point, both the molecular geometry and electron pair geometry names are the same. And that is because when we look at the central atom, the only thing that we have there are bonding electrons. So they're all basically made with the bond. That means that the atoms are attached to those electrons. So as the electrons move, so does the actual whole molecule moves the exact same way. So whenever you have a Lewis structure where you have no non-bonding electrons on the central atom, both the electron pair geometry name and molecular geometry name will be the same. So both of those names will always be the same whenever you have a situation and you have no non-bonding electrons on the central atom. Again, because they're all bonding, everybody's moving the same. So the overall shape of the molecule reflects how those electrons are arranged in 3-dimensional space. Any questions on that there? So it really is, once we start introducing non-bonding electrons into, we do get some different electron and electron interaction. Depending on whether there are bonding electrons there, non-bonding electrons there, they kind of hate each other a little bit more depending on who's there. So what they're going to be able to do is actually move a little bit more when we have non-bonding electrons, because when we have the non-bonding electrons there, there's no atom attached to them. So it gives everybody else a little bit more room for movement. And what ends up changing in that situation when we introduce non-bonding electrons is actually just the molecular geometry name. So the molecular geometry name will actually, or the shape of the molecule will actually start to change as non-bonding electrons get introduced. The electron pair geometry name will still be the same. So it's all based on, how many electron pairs you have. By the way, the bond angle is also based off of how many electron pairs you have and the electron pair geometry name. So the bond angle and also the electron pair geometry are both based on how many electron pairs there are in that atom. But as we start introducing those non-bonding electrons, that is where we're going to see some changes occur in the molecular geometry name. There's basically three types of interactions of electrons near each other, some good, some not so good. Kind of the best situation is when you get bonding electrons near bonding electrons, so like lines near lines in your Lewis structure. Those type of electrons are manageable. And that's basically what we just saw in those first few examples. There were all bonding electrons there in the central atom. The next sort of worst situation occurs when we start to get some non-bonding electrons, basically dots near lines. And because we now have those non-bonding electrons, that's going to give the molecule a little bit more room to spread out and get away from each other a little bit more. And really the worst situation you could have in terms of bonding is when you lay up some non-bonding electrons near some non-bonding electrons. So dots near dots, they hate to be near each other. And because they're really not tied down to an atom in a bond, they're able to really get out there and move away from each other a lot more than bonding electrons can do. So these differences in the repulsions that we see here between electrons and electrons is really the differences that we see and why we get some of those different molecular geometries that we talk about here. So let's take a look at the first example here, which is sulfur dioxide. And if we draw sulfur dioxide, it looks something like this. And once again here, we're going to want to count up how many electron pairs and how many bonds. Once again, we're going to look at the central atom. The central atom would have how many total electron pairs? It would be 1 electron pair, 2 electron pairs, and our double bond is going to count as only 1. So that is 3 electron pairs. In terms of bonds, it has 1 bond there. And once again, our double bond will only count as 1 bond, and it has 2 bonds. Any questions on how to count that properly? So once again, here our electron pair geometry is based off of how many electron pairs we have. And in this case, it is 3. So as we saw earlier, something with 3 electron pairs, its electron pair geometry will be our trigonal planar. But now in terms of our molecular geometry, or our shape, because we no longer have that bond here like we do in a trigonal planar molecular geometry, that's going to allow those bonding electrons to kind of move a little bit more. And those non-bonding electrons are going to kind of go up. And as those non-bonding electrons go up, the bonds are going to kind of angle down a little bit. And the molecular geometry here will end up being something known as angular. Some people do call this bent, and some people call it bent angular as well. For us in this class for lecture, we're going to go with angular for that as the name. The bond angle here is based off of trigonal planar. So the trigonal planar bond angle is 120 degrees. Because this has non-bonding electrons there, it will actually be less than 120 degrees. So it'll be a little bit less than 120 degrees in terms of its bond angle, because it's kind of missing that third bond that we see with trigonal planar. Any questions on that there? All right. The next example we're going to look at is something like ammonia. And ammonia here, if we look at the central atom, which is our nitrogen, it has, in terms of electron pairs and bonds, 1 electron pair, 2 electron pairs, 3 electron pairs, and 4 electron pairs. Again, when you're counting electron pairs, doesn't matter if they're dots, doesn't matter if they're lines, you're counting everybody, and everybody counts as 1. Number of bonds is 3. So once again, something with 4 electron pairs we saw earlier, its electron pair geometry is tetrahedral. Now with those non-bonding electrons, they're going to kind of go up, and as they do, our bonding electrons are going to kind of move down because they can sort of be okay near each other. And what we will end up getting is a molecular geometry known as trigonal pyramid. And it will have a bond angle of less than 109.5 degrees, about 107-ish in that ballpark. And it is trigonal planar because it kind of comes up this way and makes like a triangle, then this kind of pyramidal shape that occurs on the bottom of it. Any questions on that one there? So 4 electron pairs, tetrahedral, 4 electron pairs with 3 bonds, the molecular shape will be trigonal pyramid. A reminder that trigonal pyramid and the one we saw earlier, which was trigonal planar, those are different. So you got to choose, yes? So on a test or something, don't just write trigonal. And let me choose, because I'm going to choose with an X. Yeah, I can mark it wrong. So you got to choose trigonal planar, trigonal pyramid. You can't do my other favorite is trigonal. Clearly that says planar, I mean pyramid, one of those there. So, you know, you got to choose. Don't do any of those things when you're doing it. They are different in terms of their meaning. Yeah. You can, yeah. So sometimes people call it pyramid, pyramidal. It's, you know, kind of the same thing. Yeah. Other questions? Okay. All right. Lastly, here we have something like water. Water here, when we look at our electron pairs and our bonds, we have 4 electron pairs around the central atom. And we have only 2 bonds in this case. So once again, with 4 electron pairs, the electron pair geometry will be tetrahedral. The molecular geometry in this case, because it has really the worst situation, it has non-bonding electrons near non-bonding electrons. Those guys want to get as far away as possible. So they're going to kind of go this way. And again, that's going to push our bonds kind of down a little bit. And this will be bent or V-shaped. And it has a bond angle of less than 109.5. About 104-ish, no Celsius, 104 degrees or so in the case of water. So as you can see here, when we do introduce those non-bonding electrons, that is going to really cause the overall molecular geometry to change. Any questions on that there? So if we had something like this here, some of the things maybe we drew before. So for this one here, the electron pair geometry and molecular geometry should be. It has how many electron pairs? Around the central atom, it has 2, as each of the double bonds count as only 1. And bonds, it has 2 as well. So linear for both the electron geometry and the molecular geometry would be linear as well for that guy. This one here has how many electron pairs? Electron pairs is 3, as a double bond counts as just 1, and bonds is 3 as well, which means electron pair geometry here would be trigonal planar, and molecular geometry would also be trigonal planar for that second guy there. And what about this guy? This guy would be Yeah, just linear. Again, it's diatomic, so it has obviously only 2 atoms involved. Any questions on geometry? Here's a table from your book. Also, if you go online on our Canvas under exam 2 review, I made a nice little table of the geometries and all that kind of stuff if you want to look at it. But that really is sort of the best way to do it based on number of electron pairs and really number of bonds, and just sort of memorize the geometries that go with it. Any questions on that? The next thing we're going to talk about here, last thing in this chapter, is dipole moments and really molecular polarity. Now, molecular polarity is talking about the entire molecule as a whole and whether or not the electrons as a whole are being shared equally or unequally. And if it is being shared unequally, it will have a dipole moment and it will be a polar molecule. And that dipole moment is represented by that same arrow that we used when we talked about bond polarity and the differences in electronegativity values, where it points to the more negative side of the atom or the molecule, and this side is the more positive side. So polar molecules will have a dipole moment. Non-polar molecules will not have a dipole moment. They basically will share the electrons equally as a whole over the entire molecule. You could essentially think of them as being like the neutral sort of molecule. There's really no side that's more positive. There's no side that's more negative. And that's opposite of what we see with a polar molecule, where there definitely is a side that's more positive and a side that's more negative. So let's start with really the simplest ones to determine whether or not the molecule is polar or not. And that is those diatomic molecules. So if we had something like H2 or F2 or O2. In terms of bond polarity, right? Each of those bonds are polar or nonpolar. Each of those bonds are nonpolar based on electronegativity values. They would have the same. So when you take the difference, it's 0. So it would be a nonpolar bond. And because in each of these cases, that is the only bond in the entire molecule, each of these molecules then would be nonpolar. So because they have a nonpolar bond, and that's the only bond, these would all be nonpolar molecules. And that is different than when we get something like HF, which is a heteronuclear molecule. This is a polar bond, as we talked about, right? Heading towards the fluorine, which is more electronegative. And once again, because that is a polar bond, and that's the only bond we have in the entire molecule, it would be a polar molecule. So polar bond, only bond, polar molecule. So really the only place where you could use electronegativity values and bond polarity to help you decide whether or not the molecule is going to be polar is when you have diatomic molecules. And that's because there's basically just one old bond in the whole thing. And if that bond is polar, the molecule will be polar. And if that bond is nonpolar, the molecule would be nonpolar. And this guy would have a dipole moment heading in that direction, as I drew it there, heading towards the fluorine. Question on that. So those are really the simplest ones. It's either polar or nonpolar based on the one and only bond that's there. Now, if everything was like that, that would be great, but everything is not like that. So when we get to 3 or more atoms, we do have to look at a couple of things to help us decide whether or not the molecule is going to be polar or nonpolar. So with 3 or more atoms, we have to first look at, are there polar bonds? And if the answer is no, then it's going to be a nonpolar molecule. If the answer is yes, we then need to look at the molecular geometry or the shape. So for example, if we roll out our carbon dioxide that we looked at here, are there polar bonds in carbon dioxide? The carbon-oxygen bond, is that polar? The answer is yes. Carbon and oxygen, same row on the periodic table. Oxygen's further to the right, which means it's more electronegative. So if we drew our bond dipoles in this case, it would have polar bonds. Now, the geometry of this guy we just did, and the molecular geometry of this guy is linear that we just did, 2 electron pairs and 2 bonds. So essentially what we have is a straight line like my pen here, and we have oxygen pulling this way, but then we have oxygen pulling the other way, and really my pen is not going anywhere. I'm actually pulling both directions. So they actually cancel each other out. And even though that this has polar bonds, this will be a nonpolar molecule because of that, because of its geometry. Sometimes people think about polarity as like pulling on a rope. And if everybody pulls equally in opposite directions, they're going to cancel out. If everybody kind of pushes at something in equal and opposite directions, they will cancel out. But if somebody kind of pulls more than somebody else, then they will not cancel, and they will be a polar molecule. That's because these things here, which are dipoles, they are vectors in physics. Yes, they have direction, they have magnitude. Then I fell asleep in physics. But I woke up long enough to know that in some cases they do add to each other, and other cases they do subtract from each other. And that's basically what we're looking at. So in the case of something like water, it does have polar bonds heading to the oxygen. So we could draw our bond dipoles. But because of the geometry here, which is bent or V-shaped, we now have basically kind of like this deal happening, and everybody's meeting at the top, almost like you have a string on the top of something, and you just kind of pull it. The whole thing is going to move, and they actually will add to each other, and you'll get a net dipole moment happening right there through the oxygen, where the oxygen side of water is more negative. The hydrogen side of water will be more positive because of that. By the way, you add vectors, something like this, a little head to tail movement. Then the net heading in that direction is how we kind of do that thing. But let's be frankly honest, nobody wants to draw vectors or think about vectors. So there must be a much easier way to doing it. And there is, and it's really all about whether or not there's non-bonding electrons or no non-bonding electrons on your molecule. So there are certain geometries which are considered symmetrical geometries. And some of those symmetrical geometries that you learn in this class tetrahedral. Planar. It will be a nonpolar molecule. So if you had something like this here, we'll just draw not the dots on the fluorine, pretend there's dots. There is polar bonds heading towards the fluorine in each of these cases. But when we look at the central atom, I do not see dots. I see everybody on the outside is the same, which means this molecule is going to be nonpolar. And that's because all those guys are going to be equal and opposites of each other, pulling equally. They're all going to cancel each other out. Now, if I took one of those fluorines and swapped it out for a hydrogen in this case, we still have polar bonds heading in this direction. The carbon-hydrogen bond is actually nonpolar. Now what we have is all these guys kind of pulling and the hydrogen not doing much. So you could kind of imagine it would move, and it will now become a polar molecule. So if you have no dots on your central atom and all the outside atoms are the same, pretty safe bet to write it's a nonpolar molecule. If you have no dots on your central atom and all the outside atoms are different, or at least one's different, probably a pretty safe bet to write that it is a polar molecule because of that unequal kind of pulling or pushing that's going to happen. Question on that? Yeah. Yeah. So when you draw your Lewis structure on the central atom, that's always what you want to look at. There's no dots on the central atom. Yeah. Which basically means there's no lone pairs or non-bonding electrons. Yeah. 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 So the other reason, I'll get right to that right now, which is there's also unsymmetrical geometries, and unsymmetrical geometries are basically everybody else. They're basically your angular, your trigonal pyramid, your tetrahedral, not tetrahedral, I'm sorry, your bent or V-shaped. And what those all have in common is exactly what you were just describing. When you draw your Lewis structure, you got dots, and all the outside atoms are the same. So dots on the central atom, no dots on the central atom on this one. So when we do look at water, basically we see dots, we see everybody on the outside is the same. It's going to be polar. It will always lead us usually a polar type molecule. So the nice thing about that is it pretty much just leaves linear, which is a straight line. So that's pretty easy to figure out. Again, if they go opposite on linear, it's going to be nonpolar. If they head right at each other in a linear situation, it will be nonpolar. It's like two people on a swinging door, opposite sides pushing. Door's never going to open, right? It's just going to kind of sit there. The only time in a linear situation where it would be polar is if all the dipoles are heading in the same direction. Yeah, so if they're heading in the same direction, it will then be a polar molecule, which again, because it's linear, it's pretty easy to sort of figure that out. Any questions on that there? So if we go through some of the ones here, let's just take a look at some here. Again, I'm not going to draw in all the electrons here, but I'll just draw the important ones on the central atom. We did our CO2, H. All right, so obviously this one we did. That is our linear, right? So those are going to cancel. So let's go to this one, which is carbonate, not fully drawn with all the electrons. When I look at the central atom, there are no dots, right? Everybody on the outside is the same, which means this should be polar or non-polar. Non-polar, yeah. Here is this one. I see dots on the central atom. Everybody on the outside is the same. This should be, this is NH3. I see dots on the central atom. Everybody on the outside is the same. It should be polar. I have this one is going to be non-polar. Again, by the way, there's no polar bond there at all. Carbon hydrogen is non-polar. That would be non-polar as well. So that is definitely the easiest way to kind of do it, is just break it down. I see dots or I don't see dots, and is everybody the same or not the same? Any questions on how to do that there? Yeah. If they're not the same, usually it'll be polar, because usually you'll have some on the outside. Usually you'll have dots as well, but you'll have either dots, which means they're not the same, and you'll have some difference in electronegativity. So somebody's going to be pulling more than somebody else. And in the case of no dots and everybody's not the same, you usually end up somebody's pulling more than somebody else, and you usually end up being polar. Other questions on that? Questions on polarity, molecular polarity? All right, good times. All right, so that is this chapter, I think. All right, we're going to then roll into, as soon as I find it here, we're going to talk about some nomenclature. Okay, so we're going to talk about nomenclature, which obviously is naming. And we're going to talk about really the two types of naming that we are bonding that we talked about, which is ionic naming and ionic compounds and covalent compounds. It's important to know with ions, right? There's cations and anions. And when we look at the periodic table, just to make sure, I think we've talked about it, but just to double check. Everybody in group 1, if they do form an ion, will be +1. Everybody in group 2, if they do form an ion, will be +2. Skipping the sort of the transition metal region. In group 3, we're going to have plus, and that's really aluminum we're pretty talking about in group 3. We are going to skip group 4 because we do have that staircase kind of coming down through there. And in group 5, our nonmetals like nitrogen is going to be -3. Group 6, like oxygen and sulfur, will be -2. Group 7, they will be -1. So really with the negatives, we're talking about our nonmetals, which are going to gain electrons. And obviously the positives will be our metals that have lost electrons. The transition metals here can have a variety of charges. So they have a variable charge. There are 3 exceptions. There are zinc and cadmium. They will always be +2. And if you hang a leftover there by cadmium, silver will always be +1. So those 3 transition metals are exceptions. They have a fixed positive charge. But pretty much everybody else there in the transition metal region, and even outside the transition metal region, where we have things like lead and tin and so forth, they too have a variable positive charge. So they're sort of named the same way as everybody else. So that's sort of how we break apart the periodic table in terms of naming and charges. Group 1 +1 +2 +3 for aluminum, and then we skip -3 -2 -1, and then everybody else except for zinc, cadmium, and silver will have a variable sort of positive charge. Any questions on that there? Now, there are some things that have some common names, and you should go by those common names. And really on this list, we won't go with these. We'll go with these 3 for sure. If you do see H2O, it is water. It's not a trick question. Just write water and move on with your life. Yes. Nobody wants a glass of dihydrogen monoxide, right? They much rather have water, which is what we call it. NH3 is ammonia, which is not to be confused with something we'll talk about later, which is ammonium. And CH methane, that's the simplest organic molecule you have. That's basically what comes out when you light your Bunsen burner. That's the gas coming out as you light your Bunsen burner. Most people, and why I crossed down the bottom, most people for NaCl will call it sodium chloride, not really table salt. So most people will kind of go by their normal name for that. And instead of sucrose, most people will call it, sugar and stuff like that. So those 3 for sure are ones that you should know. Now, we talked about we will talk about 2 types of naming, and the 2 big categories of naming are ionic and covalent. And a reminder that ionic bonds is when we have our metal and nonmetal, and we do have a transfer of electrons, right? And that is when our metal will transfer the electron over to our nonmetal, and that will create a cation that is positively charged. And it will create an anion that is negatively charged. The other type of naming we're going to talk about is ones between 2 nonmetals, and those are covalent compounds, or sometimes people call them molecular compounds. And those are sharing of electrons, just like we talked about in naming or in bonding. Now, how we name both of these are a little bit different, and depending on the metal in an ionic compound as to how we go about naming those guys. So first, let's talk a little bit about just naming ions, which I think we did in a previous chapter, but just to review, if we have just an ion by itself, a cation, for example, which is positively charged, we do just give the whole name of the element. So again, this would be the sodium ion. If we had calcium, this would be the calcium ion. And if we had hydrogen, that would be the hydrogen ion. So as we talked about, I think in that chapter, if it is a positive ion, we pretty much just use the whole name of the metal or whatever it may be, and we just put ion at the end. When we have a non-metal, which are anions and negatively charged, those guys get IDE at the end of the name. So something that is Cl minus instead of chlorine will become the chloride ion. Something like O2 minus, which is oxygen, will become the oxide ion. So negatively charged guys from the periodic table get the IDE. You remove some of the last part of the name, a little bit more in some cases, and positive cations will just be the whole name there. When we write a formula for an ionic compound, we always want to end up at 0 charge, as we also talked about, I think, earlier. So when we put a sodium ion together with an oxygen ion, we need 2 of the sodium ions to balance out the charge. And that would give us a form of Na2O. The compound for the ionic charge, but it is made up of 2 things that does have charges. So it's made up of 2 things with charges. But when you always put a negative guy and a positive guy together, the simplest way to get to 0 is what you want to do. If you remember, that's what we talked about with bonding. That's really the basis of bonding. That allows everybody to get to the octet rule, basically, and meet the octet rule in a noble gas configuration. So again, if we had calcium and a nitrogen or nitride ion, in this case, the common number between 2 and 3 is 6. To get calcium to 6, we need 3 of them. To get the nitride to 6, we need 2 of them. That means the formula here would be Ca3 and 2 would be our proper formula. It is always the positive guy first, then the negative, both in the name and the formula. So it's always the way it goes, positive to negative. Any questions on that? Yeah. Why is it 6? So the common number what we started with was we had a calcium that was +2 and a nitride that was -3. So the common number between 3 and 2 is 6. It's the simplest way you could get it to 0, basically. So to get the calcium to 6, we needed 3 of them, and to get the nitrogen to 6, we needed 2 of them. So if you're not sure, you got to put it together to equal 0, right? So the simplest way to do that is just multiply the 2 numbers together, and that will get you the simplest number to get it to 0. Because if we just threw them together the way they were, we just like toss these guys together, we would end up with Can minus, right? And it has a charge, and you should never have a charge on a compound or formula for an ionic compound when you put them together. Yeah, and that would mean if you did that with a charge, it meant that somebody did not get to a noble gas configuration in terms of their electrons. So that's why we don't do it. Other questions? Okay. So when we talk about ionic compounds, we do break it into 2 types of categories. And these are ionic compounds. So that's our metal and our non-metal. And whenever in all naming, you have a metal involved, that is really the most important one. So that is really the most important thing to look at is the metal. And if that metal is a type 1 compound, it means it has a fixed positive charge. So those are our guys in group 1, 2, 3. Our silver, zinc, our cadmium. And if you see that, you know it's type 1. You don't have to worry about figuring out anything in terms of charges or anything like that. You basically could just go right into the naming part of it. Now, if you have a type 2 compound, that's going to be your transition metals. And just to the right, as I was talking about before, where you see things like lead or tin, kind of underneath that staircase on the periodic table. The deal with those guys is they can have a variable type of positive charge, which means you need to let people know what that charge is when you go name it. So how we do that is we'll talk about Roman numerals is how we go about naming those things, but you do have to indicate it. Now, in this case, something like chromium could be +2 in certain situations, or it could be +3. Something like copper could be +1 or +2. So naming is all telling a person like what's happening, who's involved, and because they could have multiple charge, we do have to include an additional step in the naming process. Any questions on that there? So always the metal is the one you want to definitely look at when you're dealing with an ionic compound. Here's a table as we've talked about our positive ions, pretty much the whole name. Our negative ions gets the IDE. The one exception is our good friend hydrogen. It actually go both ways. So if hydrogen is actually comes after a metal, it will actually be the negative version of hydrogen. So if you have something like LiH, that is a cation that is lithium with a +1 charge. And the anion is hydrogen with a -1 charge. So that would actually be the hydride version of hydrogen. In most cases, it will be positive, but that's the one exception where hydrogen actually will be negative if it finds itself coming after a metal that is positive. Remember that hydrogen is really a non-metal, right? So that's what happens. All right, so let's just talk about the rules for naming type 1. So type 1 is our metal and non-metal ionic compound. And once again, it is the metal here that has a fixed positive charge. So as soon as you see that, you could roll right into the name. You basically take the whole name of the metal, the non-metal gets the IDE after it, and that's all they wrote at that point. So if we look at a couple there that we saw, we have NaCl. Na is sodium, which is a metal. Cl is a non-metal. Sodium is group number 1 on the periodic table, which means it has a fixed positive charge of +1, and that means it's a type 1 compound. So we just roll with the whole name of the metal, which is sodium. Our chlorine gets the IDE at the end of it. If I had something like this, CaCl2, when I look at this, Ca is calcium, which is a metal. Cl is chlorine, which is a non-metal. Finding the calcium on the periodic table is group number 2, which means it has a fixed positive charge. That means it's a type 1 compound. And I roll right into the name of calcium, whole name of the metal, and IDE for our chlorine becomes chloride. That is calcium chloride. There is no need, and you should never ever use a prefix for 2. People like to do that and go like dichloride sounds more chemistry like. It doesn't. It sounds like an X on your paper. You do not use prefixes here. Yes, with type 1 or type 2 compounds. So if it's ionic, you should not be prefixing anything. Doesn't matter if there's 42 of those chlorines, it is still just chloride at the end of it. The cation here is calcium with a +2 charge would be our cation. The anion would be Cl-, not Cl2-, just actually Cl- would be the correct formula for the anion. So if I have this, which is Na2S, what should that be called? Yeah, so Na, which is group 1, so it's a type 1 compound. Sulfur is a non-metal, so that would be sodium sulfide. Again, here, do not have to worry about the 2. We don't use a prefix or anything like that. So never ever prefixes with ionic compounds. Any questions on that there? All right. So as we've kind of just been talking about, when we do put it together, we want to make sure we end up with no charge. But remember that the ionic compound is really made up of 2 things that do have charges. So if you are asked to write the cation or anion formula, you do need to write them with the charges. But when you put them together to write the compound formula, no charges. So if you were asked to write potassium iodide, that is what you should write. If you're asked to write the cation formula for that, that is what you should write. It should be the potassium with the +1 charge. And if you're asked to write the formula for the anion, that is what you should write. So again, make sure you keep that in mind as you go through it. Any questions on that there? All right. So why don't you try some here, give the names, and also let me give you some names and give me some formulas. Let's do magnesium oxide. And let's do aluminum sulfide. All right. Proper name on the left, proper formula there on the right. See what you come up with. Okay, let's see how you're doing. So once again here, potassium is a metal, chlorine is a non-metal. So again, we're going to look at the metal, which is potassium. That's group number 1. Tells us it's a type 1 compound. So we could roll right into the name, which is potassium chloride in this case. Again, the cation being K+, the anion being Cl- in this case. Coming here, that is zinc, which is a metal, and sulfur, which is a non-metal. Zinc is a transition metal, but it is one of those ones that has a fixed positive charge. So it does fall under type 1, which means we could roll to the name of zinc sulfide. The cation here is zinc with a +2 charge. The anion is sulfur with a -2 charge in this case. Lastly here, that's calcium, which is a metal, and bromine, which is a non-metal. Calcium being group 2, which means it has a fixed +2 charge, and type 1 sort of compound. So that would be calcium bromide. Again here, does not matter what the number is. That means the calcium is a cation, and the anion's formula would look like that, Br-, not Br2-. Yeah, so just Br-. On any of those. Now, if we have the name, we just want to put it back together. So magnesium oxide, that's a metal, non-metal. So those are going to be ions. Magnesium is group number 2, which means it should have a +2 charge. Oxide is oxygen, which is group 6 on the periodic table, which means it has a -2 charge. So to put these together, I just need one of each to get to 0, which means the proper formula here should be MgO in this case. Yeah. Question on that one. Aluminum, which is group 3, has a +3 charge. Sulfur, group 6, has a -2 charge. Again, we want to put it together, no charge. 3 and 2 means common number is 6. To get aluminum to 6, I need 2 of them. To get sulfur to 6, I need 3 of them. And now I'm just going to write the formula, what I just did there. 2 aluminums and 3 sulfurs would do it. Question on type 1. Do you need to be able to give name and formulas? Yeah. Any questions on those? All right, the next thing we're going to talk about is type 2 here. Guess I missed that guy on the bottom there, huh? That's barium hydride. So that is barium, which is a metal, and hydrogen is actually a non-metal, and it's actually the negative version in this case, which is barium hydride. And again, barium is a group 2 fixed charge, which is why it's a type 1 compound. And actually, this is a case where hydrogen is -1 in this particular case. Okay, now let's talk about type 2, I think. So type 2 ionic compounds are also ionic compounds, also metal and non-metal together. And once again, it is the metal that is the most important in that. Your metal will be a transition metal, which means it could have a variable positive charge. It works the same way, other than you need to tell the people what the charge is. So you have to do a little math maybe to figure out what the charge is, but then you incorporate it into your name. And you do that by using the whole name of the metal, just like we did before. We still do the non-metal that gets the IDE at the end. The difference is we put a Roman numeral in the middle. And what the Roman numeral indicates is the actual positive charge on the metal. Not how many metals you have, but it's the actual positive charge on one of the metals. So if we look at the example they have here, which is FeCl2, that is a metal and a non-metal, so I know it's ionic. Iron is dead in the middle there of your transition metal region, which means it's a type 2 compound. That means I'm not sure what the iron charge is, but the good thing is you will 100% of the time know what the charge is on what it's attached to. So chlorine is group 7, which means it has a -1 charge, and there's not one of them, but there's 2 of them, which means the overall negative charge is -2. So to get it to 0, the iron has to be +2 in this case. So the name here would be iron, Roman numeral 2, because of the positive charge, chloride. Once again, it doesn't matter how many of those chlorines we have, we're still not going to use any type of prefix. We have to do that because if we had something like this, Fe3 plus, or FeCl3, we would have the iron, but in this case, we have 3 of the chlorides. In this case, the iron actually would carry a +3 charge. And that means that this guy's name would be iron Roman numeral 3 chloride. Again, the 3 because of the charge. So it's important to figure out the charge and use the Roman numeral because it tells everybody what the charge is on the metal is. Yeah. No, it doesn't. No. You could go lowercase on all of them. Yeah. Let's take a look at one last one here before we go. PbO2. What is the proper name of that guy? Pb is lead, by the way, and it is a little bit outside the transition metal region, but it is named the same way as a type 2 compound. All right, what do we think the name is? Lead 4 oxide. So let's see. So we have one lead, which we're not sure what it is, but we do have oxygen, which is group 6, which means it has a -2 charge. And there are 2 of them, which means the overall negative charge here is -4, which means the positive charge on the lead has to be +4, and it is lead 4 oxide. Now, the other day we talked about that sometimes people are taught, hey, just move the numbers this way, up and down and stuff like that. And if you did it in this case, you would end up with lead 2 oxide, which would be incorrect. So remember that just moving things up and down is not always going to work. It'll work a lot of times, but not in all times. The best way is, sometimes as silly as it looks, just to draw it out like that and start counting up charges. It makes it much easier to do. That is type 2, which does need a Roman numeral. Anything in the transition metal region or outside to the right will need that Roman numeral. Anything that's a type 1 does not need the Roman numeral. Any questions on that? All right, we're laid up there for today.